So along with integer data types, we have two integer data types. I can't help it. We're going to talk binary. We're going to talk bits and bytes. And if you've sat through one of my classes before and have already heard this lecture 2-3 times, I apologize. But we have all data, and you don't have to type all these because I'm going to be typing a lot of things. All data in the computer is stored as zeros and ones. And I'm not kidding. I'm going to type a lot of stuff. I'm not expecting you to type this. Those are known as bits. Every bit can hold either a 0 or a 1. So that's 4 bits. That's also 4 bits. This is 8 bits. And so on. The more bits you have dedicated to a piece of data, the larger the value is, or the more precise it can be. So what does that mean as opposed to that, as opposed to that, as opposed to that? Well, we're going to pretend that we're hopping in a car into binary bit land. It's our bitmobile. And it's got an odometer that's only 4 digits long. And its digits can only be 0 or 1. Now, before we go very far in our bitmobile, we're going to go into our base 10 mobile. Base 10 is what we count in because of 10 fingers. If we had been gifted by evolution or God with 12 fingers, I guess we would count in base 12. So if we're going to go into our base 10 car and we start driving, the 2nd mile marker, the 3rd mile marker, the 4th mile, we know how to count. And then what happens? Well, we have maxed out that place because base 10 means a counting system where every digit is a value between 0 and 9. When we've maxed it out, we can't add 1 to it anymore. So it resets back to 0, and then the next place gets 1 added to it. Then we could keep counting, right? Trust me, I'm not going to. Now what happens? Well, we've maxed it out again, right? The maximum value is 9. It resets back to the minimum, and then the next one is added by 1. So we keep driving it until we get 0098, 0099, 009. Okay, it's happened again. We've maxed it out. So from the highest digit, goes back to the lowest, and we add 1 to the next column. But it's also maxed out. So it goes back from the highest digit to the lowest digit, and then we add 1 there. So that's how you would count in base, well, that's how we do count in base 10, and so on, right? And so then you eventually, you've driven 999 miles on it, and you know what happens next, right? And you've driven 9,999 miles, what happens next? Well, I don't know if any of y'all are old enough to have ever owned a car that had so few places in the odometer you could actually manage to roll it over. It's like they used to roll over at 100,000, and then they started rolling over to 1 million, and now they're digital, so I don't know what they do. But anyways, it rolled over. We suffered what's known as overflow. We had too much data to fill the available spot. We had 4 places of information, and all of a sudden we needed to 5 places in order to hold the data. So the rollover is called overflow. Just means that the value got too large to be stored. And that's pretty easy to demonstrate. If we load up good old NetBeans, get that loading in the background, we'll write a little program that demonstrates overflow real fast. All right, so I'm going to choose Java ANT. I don't even remember what lecture we're on.
F.
F? Yay, thank you. All right. Lecture F. I'm going to remove the package declaration, so I'm going to take out the decimal point and everything in front of it. Please create your projects in A and T if you have that option, just so that you don't have to type in this public static void main stuff. All right, so we're going to demonstrate overflow. An int can only hold up to a little more than 2 billion. A value between about plus and minus 2 billion. So if it exceeds 2 billion by too much, it's going to roll over. We're going to get corrupted data. We're going to prove that to ourselves. Let's create a variable called x and set it equal to 1. And then we're going to write a little loop that doubles that number a certain number of times. So we need a counter. Int c, short for counter, is equal to 1. While, parentheses, c is less than or equal to, let's double it 8 times. While c is less than or equal to 8, so while, parentheses, c less than equal 8, close parentheses, x equals x times 2, and then let's print it out. System.out.printf, parentheses, quote, %d space %d, backslash n. I guess we could say, you know, c equals %d, and then x equals %d. Just give ourselves a little bit better information, and then after the quote, comma, c, comma, x, in parentheses, semicolon. And then C++. Add 1 to the value of c, so that our counter, our while loop, can keep going. Camera improvement. All right. You can see what happened. After 1 doubling, it equals 2. After 2 doublings, it equals 4. After 3, 8, 16, 32, 64, 128, 256. After 8 times it has been doubled, our value is 256. But clearly that's less than 2 billion. You can double things 8 times and not run into trouble. But what if we made that like 20? I don't know what this unpacking index for central repository means. I'm going to cancel it and hope I don't regret it later. All right. Okay. So when we doubled 20 times, we got up to about, is that in the hundreds of thousands or the millions? We got up to 1 million by doubling it 20 times. What if we double it 30 times? We got up to about 1 billion. We're real close to the point where things are going to start going off the rocker. What if we doubled it like 32 times? See, we had this number that was about 1 billion. We doubled it again, and whoops, all of a sudden it's negative. That doesn't make any sense. You multiply a number by 2 and it goes negative. And then when it was doubled again, it equaled 0. And if we kept doubling it again from then on out, it would be 0. This is the point where the data corruption occurred. This is the point where the overflow happened, when our number got to be larger than 2 billion and change. It's not exactly 2 billion, that's the cutoff, but it's close. So these numbers here, we're going to see these again real soon. 2, 4, 8, 16, 32. These are your powers of 2. 2 to the power of 1 is 2. 2 to the power of 2 is 4. 2 to the power of 3 is 8. 2 to the power of 4 is 16. 2 to the power of 5 is 32, and so on. We're going to see those again real soon. So that's overflow. Overflow is what happens when your value gets too large to be held in the amount of space, the memory space allocated to it. Just like if our odometer has only 4 digits on it, we can't drive more than 9,999 files and still have it be accurate. Going back over here. That was in base 10. Let's just pretend for some reason that we have a base 4 counting system that we care about. We're never going to mention base 4 again after this next 2 minutes, but let's just pretend. Say we had 4 digits, and then we drove a mile, we drove another mile, we drove another mile, we drove another, oops. If it's base 4, that means you have the digits 0 through 3. Right? So we've maxed it out. We can't get to 4. 3 is the highest value. So it resets back to the lowest value, and the next one is incremented by 1. So we keep going. Same situation. This digit is at its max value. So it resets back to 0, and then we add 1 to the next column, and so on. And if we were counting on our fingers, we would say that this was mile 1, this was mile 2, this was mile 3, 4, 5, 6, 7, right? 8, and so on. So this is our base 10 column, but if you were going to count to 8 in base 4, you'd get a funny looking result. You'd get 20. But it's accurate. It's accurate. If you have base 4, that's how you would represent what we would call 8 in base 10. All right, forget base 4. We're not going to play with base 4 anymore, but we are going to do binary. We're going to hop into our binary mobile like we talked about. Binary is base 2. It's only got 2 digits, 0 and 1. All right, strap in, 0, 0, 0, 1. We've driven a mile. 0, 0, 0, 2. Nope, can't do that. What happens? We have maxed out. Our numbers can only be 0 and 1. And what happens when you max it out? You drop it back to the minimum and you increase the next one by 1. Now what happens? If we drive 1 more mile, what's the result going to be?
0, 1, 0, 0.
It's going to be 0, 1, 0, 0. And why is that? Because when this one increases, it can't go to 2, so it has to drop down to the minimum, and then the next one has to increase. But it can't go to 2, so it has to drop down to the minimum, and the next one has to increase. So what's the next mile marker? We drive 1 more mile. What happens?
0, 1, 0, 1.
Yep. And then 0, 1, 1, 0, and then 0, 1, 1, 1. If we kept going, it would take 8 more miles to fill them up. That's 16. Or the values 0 through 15. Right, because that's a 0. This is a 1 in base 10. This is a base 2. Excuse me, 2 in base 10. This is 3. I should have just been using tab. Told you I was going to type a lot. Alrighty then. So, what if we had some number and we wanted to know what its base 10 counterpart was without doing this counting 1 by 1? Like, what if I rattled off what is 0, 1, 1, 0 in base 2 in base 10? Now from now on, when I say base 2, I'm going to do it like this. What is 0, 1, 1, 0, parentheses 2? That means base 2 in base 10. Well, I'm lucky. I have this right here. I can look it up. Ta-da, I have the answer. But, yeah, we'll quite often have this chart, but I want us to understand how we could go from these to this without just having a little chart like we do here. And it involves powers of 2. We'll say we're switching back to base 10 because that's what we grew up counting, and we have the year 2019, What does that really mean? This place is the so-called ones place. So this last place here is 10 to the power of 0, which is 1. That's what this place is. The next one is the tens place, which is 10 to the power of 1. With me? 10 to the power of 1 is 10. Now you may wonder why something to the power of 0 is 1. Well, anything to the power of 0 is 1 for, and I've seen the mathematical proof for it, and I understood it at one time, and I no longer understand it and remember it. 7 million to the power of 0 is 1. Negative 8 trillion to the power of 0 is 1. It's just a thing. Okay, so this is our ones place, this is our tens place, this is our hundreds place, the next one, which is 10 to the power of 2. And when I say to the power of, I don't know why I'm putting asterisk. If we were doing Python, I'd put star star, and that's probably where I got it in my head. And then lastly, the 2 is the thousands place, which is 10 to the power of 3. And by the way, unfortunately, this language does not really have a power of operator. So in our code, we can't say x equals 3 caret 2. Instead, you have to use a math.pow function to take to the power of. But I think we understand what that means, so I'm going to go with that. So if we have the number 2019, what does that mean? It really means 2 times 10 to the power of 3 plus 0 times 10 to the power of 2 plus 1 times 10 to the power of 1 plus, and how many, the last one? 9 times 10 to the power of 0. Now I'm never going to do this again because this is really tedious. This is the same as saying 10 times 1,000, excuse me, 2 times 1,000 plus 0 times 100 plus 1 times 10 plus 9 times 1. Right. These are equivalent. That's the same as that, except you can't see it because it's off the... Didn't mean to knock it off the wall, but I'd like for you to be able to see the edge. Okay, so, and then if you added these guys together, if you add 2,000, right, plus, what's the next one? 0 plus, what's the next one?
10
plus 9. Then magically and miraculously we get 2019. That's what we started with. Why is it the same? Because we converted from base 10 to base 10. That's like asking Google to translate English to English. Okay. Yeah. At one time, that was a way to get around. Like if a site was censored, you couldn't get to that site. It was blocked to you, but you could tell Google, go to that site and translate from English to English, and it would show you what the site looked like. Anyways, it doesn't seem to work that way anymore. But anyways, so we converted from base 10 to base 10, but the real reason why was to get the idea of the powers. And it is so deeply ingrained into us now that we don't think of it in terms of powers of 10. I don't think, okay, if I have, $73, that means I have 7 times 10 to the 1 plus 3 times 10 to the 0. We just know it's 73, right? And it's been programmed into us since we were in the first grade or whatever. But that's what that means, the places. Base 10 is based on powers of 10. 1, 10, 100, 1,000, 10,000, 100,000. This exponent you could think of as being the number of zeros, right? There's 1 0 there. 10 to the power of 2 has 2 zeros. 10 to the power of 3 has 3 zeros. So 10 to the power of 9 would have 9 zeros after it. 10 to the power of 0, well, it's just a 1 with no zeros after it. Okay. Now back to the idea of I want to know what that number is in base 10. Well, we're not going to count in base powers of 10 anymore. We're going to set the same thing up, but in powers of 2. So we have 4 places. They're not 10 to the power of 0, 10 to the power of 1, 10 to the power of 2, and 10 to the power of 3. They're 2 to the power of 3, 2 to the power of 2, 2 to the power of 1, and 2 to the power of 0. So what is 2 to the power of 3? Well, it's easier for me if I start over here. I know that this first column is always 1. Anything to the power of 0 is 1. And then the next one is just doubled, right? And the next one is just doubled. And the next one is just doubled. Right? And if you had to keep going, if you needed 4 more bits, it'd be 16, 32, 64, and 128. You know, 2 to the power of 4, 2 to the power of 5, 2 to the power of 6. And remember on our little Java program where I said you'll see these numbers again? Well, we're starting to see them. 1, 2, 4, 8. If we kept going, there'd be a 16 and a 32 and a 64 and so on. But I'm going to leave it with 4 bits. So we have this number 0, 1, 1, 0. What does that mean? That means I'm going to write it out long form, and then I'm going to stop writing it out long form so much. That means we have 0 times 2 to the power of 3 plus 1 times 2 to the power of 2 plus 1 times 2 to the power of 1 plus, I should make it get up and do jumping jacks to wake up. I know this is but tedious. Plus 0 times 1 to the power of 0. Or we could say it's 0 times 8, right? There's no 8's in it, but there's a 4 plus 1 times 4 plus 1 times 2 plus, and how many 1's do we have? None. So plus 0 times 1. If we wanted to shorten that even more, you'd just say that that's 4 plus 2 equals 6. And if I scroll way back up to our Bitmobile, 0110 was a 6. So what if we took 1111? Without doing this business about to the power of 2, to the power of 1, to the power of 0, and so on, if we have 1111 and base 2, what does that really mean? If you write out the place values, 8, 4, 2, and 1, and you wrote 1111 underneath it, it just means that it's 8 plus 4 plus 2 plus 1. And if you added those up on your fingers or whatever, you get 15. How about if you have 0101? What does that equal to?
5.
Yep, a 4 plus a 1 is 5. How about 1110? Well, if I put 8, 4, 2, and 1 above it, that makes it pretty easy to figure out.
14.
8 plus 4 plus 2, and then there's no 1's, so if it was longer, like that. Say we had 8 digits rather than just 4. Well, you just have to have more powers, right? 1, 2, 4, 8, 16, 32. Well, that's not working. 128, 64, 32, 16, 8, 4, 2, and 1. Those are our 8 places. So, I can't add up in my head, but Shannon can, but whatever that is, right?
We just did this in another one of my computer classes.
Yeah. So, I'm going to cheat. Oh man. Okay, fine. There's even a calculator program on Windows that you could do these things. 212. But, you know, it's 128 plus 64 plus, are there any 32s?
Yeah.
There's no 32s. Are there any 16s?
Yes.
There is a 16. Are there any 8s?
Yeah.
Am I hearing when I'm thinking there ought to be a There's no 8s. Are there any 4s?
Yeah.
There's a 4. Are there any 2s? Nope. And are there any 1s? No. Okay, so, and then supposedly that's equal to 222 or whatever the converter said. 212. All right, we could go further on this, but the thing that I wanted to show you is that 111 is equal to 15. But if we had all 1s for 8 bits, that's equal to 255. Just take it on faith. If you have 16 bits, so 4 bits, the max value is 15. 8 bits, the max value is 255. How would I calculate those? I would just add up 1 plus 2 plus 4 plus 8. And then to calculate that one, it would be 1 plus 2 plus 4 plus 8 plus 16 plus 32 plus 64, right? Out to 8. 16 bits. The max is, I believe, 65535. And so on. The more bits you dedicate to it, the larger the value that can be contained in it. There's a formula for showing the maximum value. It's 2 to the power of the number of bits minus 1, where n is the number of bits. So 2 to the power of 16 minus 1 should give us 65535, unless I'm confused. 2 to the power of 16 minus 1, 65535. So your old Nintendos, when you were a kid, they were 8-bit computers. 8-bit chips inside them. So they could only display from a palette of 255 different colors on the screen. And it was actually a lot more limited to that than that. They probably only displayed like 16 different colors on the screen, but those colors could be chosen from a palette of 255 colors. And the number of pixels wide may have been 256 wide, you know, or 256 tall or something like that. And the reason that it had those limitations is that it was 8 bits was dedicated to that data. And the good old game Pac-Man. Pac-Man could only play for 255 levels because only 8 bits were dedicated to holding the level counter on it. Some video games, you know, that was the maximum number of extra lives you could earn was 255. And past that, you know, you couldn't do anything else. Back in the old days, 8 bits is a byte. And so the maximum value of 1 byte is 255. And 0 to 255 gives you 256 different choices. 16 bits would be 2 bytes. The max value of 2 bytes is 65535. My keyboard repeated. 65535. Your Sega Genesis and your Super Nintendo were 16-bit computers. They could display much prettier pictures. Higher resolution and the color palette, you know, picking, you know, from 65,000 different colors rather than just 255 colors, so the graphics are much prettier. Then the PlayStation came along and it had 32-bit graphics, and so the colors were, you know, fantastic and stuff like that. So, what if you had 4 bytes to play with? That's 32 bits. So what's the max value of those? 2 to the power of 32 minus 1. I'm going to have to type that into Google. But it's going to be about 2 billion. I lied. That doesn't look like 2 billion to me. Oh, it's 4 billion. So why is our limit 2 billion? We'll get into that. We're going to say 2 to the power of 32 minus 1 is about 4 billion. So maybe you remember hearing about Windows is 32 bits, and then they came out with a newer version, and the 64-bit version of Windows, because my processor is better than it used to be. My Pentium was a 32-bit Pentium, and now I'm using this, Core Central whatever. That's a 64-bit whatever. So, pretty much all the computer hardware you buy anymore is 64 bits. So you install the 64-bit version of NetBeans and Visual Studio and this, that, and the other, and 64-bit versions of Windows. One of the limits of having a 32-bit computer is that the amount of memory that it could address was limited to 4 billion different bytes, right? So if you had a laptop, a 32-bit laptop, it didn't do you much good to install more than 4 gigabytes of RAM in it. That was a real strong, compelling reason to come up with an operating system that wasn't just limited to 32 bits, but was a 64-bit operating system, so that it could access larger amounts of RAM than just 4 gigabytes. And so if you had an 8-bit a 64-bit operating system, 64 bits, how many bytes is 64 bits?
8.
Yeah, 64 divided by 8. So that's 8 bytes. And so that's 2 to the power of 64 minus 1 being the largest value. It's going to be astronomically large. Big number. 1, 8 followed by 17 zeros. One, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, right, well, whatever, right. Let's do 1.8 times exponent to the whatever Google just said, 19. Huge number. We're not going to be able to max out the RAM that a 64-bit processor, when I say we, I mean the people who invent, computer hardware, for a long time. 32-bit, only being able to access 4 gigabytes. Yeah, that was a limit that people hit pretty soon. Poor Bill Gates said that no computer would ever need more than 640 kilobytes of RAM. That's why the old DOS computers, the first PCs, only had 640 kilobytes. That has to be facetious. He cannot possibly have said that. He must have just said that it's enough for now. Anyways. So, the more bytes you have dedicated to a piece of data, the larger piece of data can be stored in it. An integer is a 4-byte value that can hold a value from negative 2 billion to positive 2 billion. A little bit more. Because the maximum value that can be stored in 4 bytes is 4 billion, but that's 0 to 4 billion, right? That doesn't help us if I want to record negative numbers. So how do they get negative numbers out of this stuff? What some clever engineer decided is that if you had some number like this, 0, like if you had a 4-bit value that could count from 0 through 15, right? Like that. You could instead say the first bit means that it's a negative number. And if the first bit is 0, it's a positive number. And if the first bit is 1, it's a negative number. Now it's slightly different than that. That's not 100% accurate, but it's instead it uses something called 2's complement to get it. But it's the idea. So you could count up to where you had the last 3 digits represented your data up to 7, and then the next bit, the first one, dictated whether it was a positive 7 or a negative 7, right? So by using the first bit as a signed bit, you could get from -7 to +7. Makes sense? That's why we can do from -2 billion to +2 billion when I said that the largest number that 4 bytes could hold is 4 billion. Now some programming languages, the C, C++, and C# programming language let you create what are known as unsigned integer values, where you say, no, I want every last bit to be used for my number. None of this using the first one for a negative number. So those data types can only support positive numbers. They can't count negative, but they can get larger, right? You can get up to 4 billion if you had an unsigned 4-byte value. So an int is a 4-byte value. A long is an 8-byte value. Let's find out what the maximum value of a long is. These are constants that are built into the language. We can make it print out the maximum value of a long. System.out.println, parentheses, quote, the max of an int is space int quote plus capital I integer dot max value. I don't know why I didn't take it when I double clicked on it, but there we go. That's the maximum value of an int. Let's do the same thing for a long. System.out.println, parentheses, quote, the max value of a long. Long just means more bytes. It's an 8-byte integer rather than a 4-byte integer. So the max value of a long is space end quote plus long with a capital L dot max value. So we should see that the max value of an int is about 2 billion, a little more than 2 billion, and the max value of a long, that big number. 9 to the power of 19 or something. I mean, exponent 19. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19. So, a long is an 8-byte value which can count like plus or minus, I've already forgotten. My short-term memory is so messed up. 9 to the power 9 exponent 19. So plus or minus 9 exponent 19. If you need a number that's larger than 9 exponent 19, you can't use an integer anymore. They haven't made a 16-byte int or a 32-byte int or anything. Instead, how do you get large numbers in our world, in the real world? If we want to express a number, we start using exponents, right? The number of copper atoms in a pound of copper, you express it in some kind of notation like this. 3 exponent, 32 or something like that. That just means, I said 3, a 4 followed by 32 zeros, right? That's short form for 4 times 10 to the power of 32. And if you have floating point numbers, great, right? Anyways, you can make very large numbers by increasing that exponent. 4e to the 99 is a great big number, right? It's 4 followed by 99 zeros. So you can get huge numbers by using exponents, much larger numbers than you can store even with longs. So a float is a 4-byte floating point value. I'm going to say an int is a 4-byte integer and a long is an 8-byte integer. I'm going to revise my notes. If you have been typing in any of these, you certainly do not have to. And then a float is a 4-byte floating point, and a double is an 8-byte floating point. Now the fact that it's floating point means that some of its data is dedicated to using exponents. Now what if you had 8 bits, an 8-bit float? This is kind of a silly idea, but the first 4 bits might be the number, and then the second 4 bits might be the exponent. And so the largest value you might be able to have would be, 7 to the power of 7, something like that. Right. These numbers here could control the first part, and the next digits could control that one. Now it could be that you've decided that you don't care about having exponents that much, so you may say, okay, well, I'm going to use the first 6 digits as my data, and then the last 2 digits are going to be dedicated to my exponent, and that way my numbers can be a little bit more precise because I can have 6 digits of accuracy rather than just 4. So the designers of the floating point types had to make a calculation, how many of those bits to dedicate to exponents and how many bits to dedicate to the, and I can't believe that I forgot the term for the thing in front of the exponent. Arg. I'm coming up with completely wrong words like meniscus, which is a chemistry term for rounding of water. Yeah. What is it? It starts at an M. Okay, fine, they're calling it the base. There's a different term. The coefficient, the base, and the exponent. Okay, so this one's saying coefficient. That's actually not the term that I was thinking of, but it'll work. So you could dedicate 6 bits to the coefficient and only 2 bits to the power, But anyways, a certain number of bits in it are dedicated to the coefficient, the first part of the exponent, and the second, the rest of it is dedicated to the rest of it. There's a limit, right, to how large and how precise a float can get. A float has about 7 digits of accuracy, of precision. And the largest exponent it can support, I believe, is 34. Let's prove that. Let's go here and print out the max value of a float. System.out.println parentheses quote. The max value of a float is space end quote plus float with a capital F float dot max underscore value. Yeah, e to the 38. So it has about 7 digits of accuracy and supports exponents of up to 38 or negative 38. So 38 zeros after it, or point, with 38 zeros followed by your little piece of data. So float is a 4-point floating point with 7 digits of precision and a max exponent of 38. A double is an 8-point floating point with about 15 digits of precision and a max exponent of 308. Really, for all I want you to remember from now on, I want you to remember the binary stuff, and we'll probably go back to it or whatever, is why a long holds larger numbers than ends. It's because there's more bytes dedicated to them, so the powers of 2 go up higher. And why double is a better type than float. It's got extra bytes dedicated to it, so it can hold a much larger exponent, and more digits of precision. And hopefully you know what digits of precision means. If you have a float and you want to get really precise about something, if you only have 7 digits of precision, you could only do this. 8.1, 2, 3, 4, 5, 6. I've used up 7 digits there. Now it doesn't matter whether that's, to, the power of 38 or the negative 38 or whatever. That's all a float can do. A float can't get any more precise than that. A double has more digits, right? 15 digits of precision. So 8 dot 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, like that, right? Much more precise. Times 10 to the power of 308 as being the largest one that it can hold. So doing math where all your numbers are getting rounded off to 7 places of precision, floating point errors happen really fast. Rounding errors happen really fast. They are much less visible if you have this many digits, that you can play with. So doubles, just use doubles as a matter of course. Don't ever even type the word float into the language. Just always use doubles unless you have some strong, profoundly compelling reason to say, you know what, I really don't like accuracy in my program. I think I'm just going to use float today. Alrighty, I hope that was a gripping and exciting lecture. Sometimes I give people a worksheet to fill out to show that they have the concept of converting binary to decimal. What if you needed to do the reverse? What if you had the number 76 in base 10 and you wanted to convert it to binary, to base 2? Well, there's a little process for doing it. And what I would have done before I learned this process is, knowing those powers of 2, I would have said, what's the largest power of 2 that'll fit into 76? It's 64. Okay, so there's a 64 in it. And then are there any 32s in it? No, because anyways, there's a algorithmic way of figuring it out. What you do is you just start dividing the number by 2 and keeping track of the remainders. So 76 divided by 2. 76 divided by 2, I think, is 37, with a remainder of 0. 37 divided by 2, 18, with a remainder of 1. 18 divided by 2 is 9, the remainder 0 because it was an even number. 9 divided by 2, I should not have written so large because I'm about to run out of space already. 9 divided by 2 is 4 with a remainder of 1. 4 divided by 2 is 2 with a remainder of 0. 2 divided by 2 is 1 with a remainder of 0. And then 1 divided by, how do you like to get exposed? 1 divided by 2 . I'm confusing myself here. 4 divided by 2. 9 divided by 2 gives you 4, the remainder of 1. 4 divided by 2 gives you 2 with a remainder of 0. 2 divided by 2 gives you a 1 with a remainder of 0. And then 1 divided by 2 is 0 with a remainder of 1. And then you just write them, but you write them from the bottom up. So 1, 0, 0, 1, 0, 1, 0. If I hadn't made them look like 6s, it would have been a lot better. 1, 0, 0, 1, 0, 1, 0. If we took the time to figure out what that is, it would add up to 76. I wonder if that's even true. Is that right? 1, 2, 3, 4, 5, 6, 7? Yeah, because that's the 64's place, so there's a 64 involved. But there's no 32s, there's no 16s, there's an 8, there's no 4s, but there's a 2. And so 64 plus 8 plus 2 is 76. So that's how you convert from a base 10 number to base 2, is by doing this divide by 2 and write down all the remainders business. I'm never going to ask you to do that, but that's how you do it. All right. Now what did that have to do with Java? Well, you needed to have the idea of overflow. You needed to have the idea of choosing a data type large enough to hold your number. You don't just need to arbitrarily say, I'm going to put everything in a double because I'm afraid that the numbers aren't going to get large enough. If you're counting, somebody's weight, It's probably not going to get over 2 billion, so it's probably safe to leave it as an int. If it needs to be fractional though, somebody needs to record, you know, that that they weigh 183.56 pounds, then yeah, you'd use a floating point type. And in that case, just always choose double. So use int, and I know I've said this before. So for whole numbers, use int unless the number needs to get above 2 billion. Then use a long. For fractional numbers, for floating point numbers, for decimal points, use double. Just flat out. Alrighty, and is there any homework that I could have assigned based on all of that lecture? No, really not. But do we have something queued up that is similar to what we have already been doing? Let's take a look. Believe it or not, there's a part 2 to this lecture, but we're not going to talk about it. It's called hexadecimal. ASCII hex binary worksheet. Let's pretend that this was our homework assignment. Let's just take a look at what your evil professor would have made you do if he had assigned the ASCII hex binary worksheet. Well, we can't do some of it because we haven't covered ASCII and we haven't covered hex. But we can do some of these things. I ought to make you do this. I ought to be mean. But nah, because we've only done the first part. We can't do the rest of it. So let's just do this by hand. Let's just do this all together. Binary to decimal. Translate these binary values to decimal in the fashion that we've learned in class. The first 2 are done for us. Looks like the first 3 are done first. Your professor can't count. 1, 1, 0. Well, if you remember the powers of 8, 8, 4, 2, and 1, then there's no 1s, but there's a 2, and then there's a 4. So 2 and a 4 is a 6. How about this one? There's a 1s place, but there's no 2s, and then there's a 4, and then there's an 8. So 1 plus 4 plus 8 is 13. Here we have a 1s, but we have no 2s, we have no 4s, we have no 8s, but we do have a 16. So 16 plus 1. So what have we got here? Somebody read out the numbers involved here. And I don't care, it's actually easier if you just go, right to left. Because that way, if you don't remember, that large value. So this is the 1s place. So we do have a 1. Do we have any 2s?
Yes.
Do we have any 4s?
No.
Do we have any 8s?
Yes.
Okay, and so that looks like it's about 11. How about this one? Read these off to me, starting with 1. Are there any 1s?
No.
Okay, but we have a 2. What's next?
4, 16.
22 then. And that one's just straight 1 plus 2 plus 4 plus 8. $31. How about that one? I think I heard it. A 4 and a
16.
Yeah, 4 and a 16. How about that one? Well, that one's easy. And this one. There's a 1 plus a 2. No 4s, no 8s, no 16s, no 32s, no 64, but there is a 128. Make sense, gang?
Mm-hmm.
Save the rest of this for some other day. Oh, I know what we can do. Let's go and look at the Chapter 2 quiz. We're done with Chapter 2. Now the quizzes, You can do them anywhere. You don't have to go to the library or do them or whatever. And you can take them multiple times because I want you to get a good grade. They are learning tools rather than measuring tools. The exams measure, but the quizzes are learning tools. Think of them as, people ask for, I want to practice exam. Well, I don't give out practice exams, but you have these quizzes. So why don't we work on Chapter 2's quiz together? Do I have to go into student mode? No, I can click preview. So everybody can see the quiz? If you click on, no, you can't see the quiz because that thing's grayed out. Maybe it's under assignments though. If we look under assignments, do you see the quizzes?
There's, I see something that says on my to-do list, Chapter 2. I think it's the quiz.
Okay, yeah. So go to your to-do list, click on Chapter 2. I'll make the change necessary for the quizzes link to show up for you as well as for me. And let's take it together just to, alrighty. Explain what this pseudocode statement does. Print account number equals plus account number. Ew, I hate essay questions. Well, most of the time the things are going to be like multiple choice or whatever. But what does that do? It displays the string account number, or the text if you didn't feel like using a fancy word like string, followed by the value of the account number variable. And I'm not going to put that question on the exam. Remember, Chapter 2 didn't have hardly any Java in it, neither did Chapter 1. That's why we're going to do this stuff together. Knock it out of the ballpark, and then it's not going to show up on the exam most likely. Provide an appropriate, well, although this one might. Provide an appropriate variable name for a variable that holds the average of a series of scores. Okay, here's a lame variable name, A. That's also pretty lame, AVG. But if I was demonstrating code in class, I probably would use something like that. Average score. That's a way better variable name. Or whatever, right? I mean, you can come up with your own, but this is what the book is recommending, is that we use something called camel case, where you use capital letters, in the middle if you have extra words in it. All right, I'll let you do this one on your own, just to see what you come up with. Give a variable name for a variable that holds profits earned in 2019. The only key to remember is that a variable name cannot begin with a digit. So 2019 profits is not a good variable name. It would be a syntax error, it would not compile. But come up with one. A variable name that means profits earned in 2019. And P would not be adequate, right? No single letter variable names. Write a line of pseudocode or Java that tells the program to perform the operation mass multiplied by acceleration, and then assign the result into a variable named force. Well, to do this in Java just means we're going to add a semicolon to the end of it. So let's assume that these are our variable names. What's our expression going to look like? The result's going to be held in a variable called force. So force equals, and then what's next? What's the rest of it? Yep, mass asterisk acceleration. Write a line of pseudocode that tells the computer to put user entry input into a variable named age. I think it would just be input age. We're not learning pseudocode. That's not the point of this class. What are the 3 types of flow control described in Chapter 2? Now this is actually supposed to be an essay question so that we had more room to type than just this one little bit of line. But what are the three types of flow control? Now, if I give you the wrong answer, it's because if I wing it, I'm going to give you the way that they're worded in Fundamentals of Programming. And so instead, I want to look it up. Flow of control. But somebody knows, right? If statements are one form, and then there's others. There's sequential statements, there's branching, and then there's loops. So back to our quiz. Sequential, branching, and loops. Fundamentals call that decision instead of branching. And your professor would argue that function calls are a fourth kind of flow control, but the book doesn't say so, so let's just leave it at that. What are the three types of loop termination techniques? Well, one of them is Sentinel value. But then there's two other forms of loop termination techniques. And what is loop termination technique? Just how is a loop going to know when to stop? One is a Sentinel value. Enter your bowling score, or -1 to quit, that kind of thing. Let's go see what the others might be. Go away. I said, go away. All right. So, we need to find loop termination. So I'm just going to Control F on the word loop, and on your exams and your quizzes, you're allowed to use your PowerPoint. Okay, this is taking longer to find than I thought. If I just looked up the word Sentinel, it would take me straight to the answer, so I'm going to cheat. Sentinel. Here they go. Three types of loops. Counter loops, user query loops, and Sentinel values. Now when I said you wouldn't see these questions again, you're going to absolutely see this question again, like on a midterm. And just tuck that away. That's pretty important. You need to know the three basic ways. I should throw this question in on the Chapter 3 quiz as well, because since I already told you Chapter 2 is kind of meh, but this is important. So let's go and fill them in. Counter, user query, and Sentinel values. Three ways to do the termination of a loop. Counter just means, okay, you're going to write a loop that goes from 1 to 10, and that's it. User query is you ask the user if they want to continue. That was fun. Do you want to play again? Yes, no. Right? That's user query. And the Sentinel value is when you have a special value that means stop. Enter test score, or -999 to exit. What is a Sentinel value, by the way? There's 4 answers here. I bet somebody can tell me which one's correct. Exactly, signal the end of input. Type in your test scores followed by -999 to quit. The -999 is the end of the input. That's the Sentinel value. Describe in a sentence or two what an infinite loop is. Well, we could look it up in the PowerPoint. I could give you a definition. We could just say an infinite loop is a loop that never stops. That's kind of lame. We're going to get a little bit better than that. An infinite loop is a loop. Well, why don't we look up their definition for it? It's possible for a loop to repeat forever. It's called an infinite loop. An infinite loop is a loop that repeats forever. Technically, it's because its loop condition never becomes false. So, as far as notes are concerned, well, here we go. What will y equal when this code is done? Don't type it in and run it, just estimate. Okay, so X is a counter, and it starts off at 1, and it counts from 1 to 5. Y is a number that gets 10 added to it each time X goes up by 1. So if we add 10 to something 5 times, because the loop repeated 5 times, then what's that number going to wind up being? Started at 0 and we added 10 to it 5 times, then what's it going to be?
50.
Yeah, it's going to be 50. All right, then we ought to be able to submit the quiz. So as far as notes go, even if you didn't type in anything else, you don't have to type in anything at all, right? You can just fill in a little thing, you know, that said you were here. But I do want you to remember Sentinel value. Sentinel value ends a series of input. 3 types of flow control: sequential, branching, and what was the third one? Looping. Yep. And then 3 forms of loops are counter, or 3 forms of loop termination, counter loops, user query, and Sentinel value. There, those are our notes for today. We talked an hour and a half, got 3 notes. But it was more interesting than that. All right, so I have to grade the quiz by hand. Even if it's all multiple choice and stuff like that, I still have to grade it by hand to make sure that it's not marking things wrong. Anything where you type in data yourself rather than just picking multiple choice or true false is likely to count as wrong. So when you submit a quiz and you see a score, just don't take it as a score. Just take it as, oh, well, that the computer made up a number, then I have to go and grade it and give it a real score. And of course, everybody's going to make 100, right? I mean, on this one. All righty. No homework. And we'll get back together on Thursday and start learning Java again.
Is there are you going to create a Dropbox?
Oh, a Dropbox for this. Yes, please. Yes, please. All righty.